Okay, let's have a look at proving whether some functions are one-to-one and onto. So, is the function from the integers to the integers defined by f of x is equal to 2x one-to-one and onto? So what is this question really asking us? Well, we're asking that it has to be both one-to-one and onto. We're not going to check whether or not this is a subset of the integers to the integers. We're going to assume that that's true for all of our questions, and we're just going to assume that this is in fact a function. So all we're going to do is we're going to check these two statements. Let's go ahead and give that a shot. Okay, so first let's go ahead and check whether the function is one-to-one. So let's look at this and think to ourselves, what does it mean for something to be one-to-one? Well, it means the following. This is our definition of one-to-one. This means that if we have two things that are equal in our codomain, our 2x, then it must be that in our domain they are also equal. And of course, okay, so this is our definition of one-to-one. So what is it saying? It's saying, okay, so this is our definition for a one-to-one, and what it's saying is that if we have two things in the codomain, our 2x, that are equal, then it must be that our elements in our domain must have also been equal. And of course, the elements we're looking at must be integers. So what does this mean? This means that if we plug in, let's say, f of 1, and we're saying that's going to equal to 2 times 1, which is equal to 2, we're saying, okay, well, if we have some other integer, like let's say b, and that's also equal to 2, since f of 1 is the same as f of b, since they're both equal to 2, then it must be that 1 is equal to b. That's what we're saying. We're saying there's no other possibility. B cannot be something like 2 or 3 or -1 or 0, because none of those are going to be equal to 1. So that's what this is saying. And now looking at this function that we have here, I think that's going to be true, because if you plug in any integer here, you're going to get a unique integer out. That's what that really is saying. So we've already tried 1. Let's go ahead and try 0. If we plug 0 in, what are we going to find? Well, it's going to be 2 times 0, which is going to be 0. And I can't think of a different integer that we can plug in here that's also going to give us 0. So that's also looking distinct. Let's try a negative number. Let's try something like -1, right? Well, that's going to be 2 times -1, which is going to be -2. So generally speaking, from these examples, it looks like that, yes, it is one-to-one. So in that case, we're going to say that it's probably true that it is one-to-one. But we can't now say the statement is true. We have to now verify that it is in fact onto as well. So what does onto mean? This down here is going to be our definition for what it means for a function to be onto. It means that every single integer in our codomain, every single integer can be achieved from our function given an x. So this means that there exists some input always that'll get us any integer in our codomain. Our codomain, of course, is going to be all the integers. So what does this mean? This means that we're looking to be able to get all the integers using this function. Now, I'm already suspicious of this claim, because what does 2 times x look like? It looks like our definition for what an even number is. So this makes me think that, well, it can't be possible we get all the integers, which is what our codomain is, because all the integers includes evens and odd numbers. So I don't think we can get odd numbers, but let me go ahead and show you what I mean. So for our onto verification, let's go ahead and plug in 0. That's going to be 2 times 0, which is going to be 0. Let's plug in something like, or no, sorry, we have to think about this backwards, right? We have to be able to say that 0 can be gotten from 2 times x. We have to say 1 can be gotten from 2 times x. 2 can be gotten from 2 times x. 3 can be gotten from 2 times x, so on and so forth, and similarly for the negative numbers. That's what it means for it to be onto. We can get every integer in our codomain. So can we get a 0? And the answer is yes, because x here would have to be 0, which is also an integer. So yes, that's true. Can we get a 2? Well, yes, because x here just has to be 1, which is in fact an integer, so yes. What about 1 and 3? Well, in order for us to get a 1 from 2 times x, x would need to be 1/2, which is not an integer. So this means we cannot get 1 from our function, because when we put in an integer, we will always be getting an even number. If we want to get an odd number here, we would need x to be a real number, not an integer, which means we cannot have the codomain of integers. Similarly for 3, in order for 2x to get us 3, x would need to be equal to 3/2, which is not an integer. So that means that, no, it's not true that we can get every integer in our codomain with an integer in our domain using our function. Specifically, we cannot get odd numbers from a single integer. So let's go ahead and write down the proof for this. So first thing we say is we say, let f be a function from the integers to the integers such that for some x in our domain, f of x is equal to 2 times x. So we've defined what our function is in our proof. We say, then f is 1/1 because, and now note, I wrote down the contrapositive of our 1/1 definition because it's going to be easier to try and prove this. So what does this mean? We're saying because is 1/1, we'll just put a full stop there actually. So let me rewrite this a little bit neater, let me organize this better. So we're saying f is 1/1, and we say let a and b be in our domain such that the codomains must be equal. So we've supposed this part. Now we want to prove that when this is true, this must be true. For all a, b, of course. So then what are we saying? We're saying then f of a is equal to 2 times a, and f of b is equal to 2 times b. So 2a is equal to f of a, which is equal to f of b, which is equal to 2b. Thus, 2a is equal to 2b. Dividing both sides by 2, we get a is equal to b, making f 1/1. So there we go. We've shown that it is true that it's 1/1 for all integers a and b, because we've shown that when this is true, this must be true. So there we go. So we've shown the first condition, but of course we know that this is false, right? So what are we going to say? We're going to now try and show that it is not onto. So we say, however, f is not onto because, okay, so now we're disproving something, and how are we going to do that? Well, onto is a for all definition, so in order to disprove our onto, we have to use the negation, which is going to be there exists something in the codomain such that there does not exist something in the domain to get it with our function. So we're going to say because there exists a y in our codomain such that x is not an integer when f of x is equal to 2x. For example, and of course here we can use our example that we came up with earlier, if y is equal to 1, then f of x is equal to 1, which is equal to 2x. So x must be equal to 1/2. and 1/2 is not an integer, so we can say 1 cannot be obtained from an integer x from the function f of x is equal to 2x. So there we go. What have we done? Well, we've shown that our red statement, which is going to be this part down here, or my bad, this part down here, is true, but then we showed that this last half is not true. Now, in reality, to write a proper proof, you could have absolutely just gotten to here. You didn't need to write the red side. You could have just said, the statement is false because it is not onto, and then you could have explained how it is not onto. But I wrote down the red so you can kind of see how you would also prove something is 1-to-1. So there we go. We've proven that this statement is not, in fact, true.